Welcome to the electronicshobbyblog.com. For our first Let's Build project, I've chosen a decade resistor substitution box. Those of you who went through the first few lessons on resistors noticed that when it came to the lab segment, we needed a few resistor values that we just didn't have in stock. And so rather than having to wait and order them or jury rig something out of some other resistors, I was able to pull out my handy Heathkit resistor substitution box, dial up the values we needed, and we were able to continue with our work in the lab. So I thought, it would be really handy for other hobbyists to be able to have a good quality resistor substitution box. So I started looking at what was available online, and I was really surprised and disappointed by what I found. First, any good quality resistor substitution boxes that I found were very expensive, $200 or more. And the ones that were much more affordable in the $50 or $60 range really weren't very good. They had extremely limited number of resistors. Many of them were just standard values switched, or they had very low power handling. In fact, even the more expensive ones didn't have power handling better than about half a watt. So I started thinking, I'll bet we can build our own decade resistor substitution box for a lot less than the expensive ones and make it just as good, if not better. So let's look at some design requirements before we get started. So let's look at our requirements. First, we want 6 digits of resolution, so 6 digits. And we want the box to have a range of 1 ohm to 999,999 ohms. Now, if you want to add a digit at either end, you can feel free to do that and have a box that goes from 0.1 ohm up to 9,999,999.9 ohms for just a little bit of extra money. But I'm trying to do this to keep the cost down for hobbyists. And so I'm going to limit mine to that value. And of course, you can add, like I said, a digit at either end. It just takes a couple more rotary switches and the appropriate resistors. Second, we want a 3-watt power handling capability. So like I said, even the expensive boxes I saw were limited to half a watt power handling. We're going to build ours to handle 3 watts. Third, we want to use at least 1% tolerance resistors. So like I said, you can go all the way down to 0.1% tolerance, but we're going to design ours for 1% tolerance, again, to keep the cost reasonable. 4, we want it to have a professional look and feel. So we're going to design something and make some design choices so that the box looks and feels like a quality box. 5, we'll be able to hook up easily with binding posts so we can use either wire or banana plugs. So that's our design too. So let's get started on the design. So design-wise, we need to make a design decision right up front. There are a couple of choices when it comes to what type switches to use. Right? There are thumb wheel switches, which can be nice, and they're digits, and you just kind of thumb them up, right, a little bit. And actually, a thumb wheel switch kind of looks like that. It's got a digit, and then usually a little thumb wheel on the side. Well, the catch with those is they tend to be very expensive. So we're going to kind of rule those out right away, and we're going to go with a standard rotary switch, which is what you saw on my Heathkit Decade resistance box. That'll help us keep the cost down, and they're pretty good quality. But we need to talk a little bit about how they work first and the types of switches we need. First, we know that each one of our rotary switches needs to choose between or select between 0 to 9. So 0 to 9, that's 10 positions. So whatever rotary switches we choose need to have a minimum of 10 positions. Now they come in all types of numbers of positions. So there are 10s, 11s, 12s, going all the way up to 20 or so, even more. So we're going to go with 10 or look for 10. But you know what? If we find some good 11 or 12s that are cheap and we can get a bargain on them, we may use them and just leave the last 2 positions unused on the switch. Second, we need to decide how many poles our switches have. So we're only switching one item at a time, so one signal, and so we only need single pole rotary switches. And so there are rotary switches, if I draw that, have 2 poles, 3 poles, and so you'll have multiple set of lugs coming off, and these are called decks. And so usually multi-pole switches will have multiple decks. And so these are often used for switching stereo, when you need to switch more than one channel and have the channels remain independent. Well, luckily, we only need 1 pole switches. We only need a single deck for that 1 pole. So those are the cheapest kinds of rotary switches. So we're in luck there. The second thing we need to talk about is there are actually 2 types of rotary switch. One is called shorting rotary switch, and it's also called MBM, abbreviated, or make before break. MBB, sorry. And then there's the non-shorting switch, and the non-shorting type switch is called break before make, or BBM. So you've got MBB and BBM are the 2 types. So with a shorting rotary switch, if we look at the rotary switch, and the rotary switch has terminals going around, and then like a potentiometer, it has a wiper, which is your central terminal, and then the wiper is actually what makes contact with the contacts for the switching. And so a shorting switch will actually make the contact with the next terminal before it breaks the contact with the previous terminal. And so the reason it's called a shorting switch is because there's a momentary short created between these 2 contacts before it switches. Now, with a break before make type switch, it actually the wiper leaves this contact before contacting this one. And so what you're getting is you're getting a momentary open circuit rather than a momentary short. So in a non-shorting switch, the 2 terminals, adjacent terminals that are being switched between, are never shorted. And so we're going to want non-shorting switches. So just a little bit of a spec. We want 10 position, single pole, single deck rotary switches, and we want non-shorting rotary switches. So now let's do a little bit of the designing of our circuit. Let's look how we need to wire up these switches to allow them to switch the resistance the way we need it to be switched. So if we consider a rotary switch, I tell you the rotary switch has terminals. And in our case, there'll be 10, and it has a central wiper. And we're going to call this position 0, 1, 2, 3, 4, 5, 6, 7, 8. And there's our 9 position, so our 9th position. So we have 10 positions around this. And then what we're going to do is we're going to make this one of our terminals and this one of our terminals, and we're going to wire a resistor right here. Then we're going to wire another one here, 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 and so on and so on. So let's take a look at how this works. So assuming we're in position 0, let's trace the current. So we're in position 0, and the current's going to flow in through the wiper and right out. And so there are no resistors in the loop. So when we're in position 0, the resistance equals 0, which is exactly what we want. Call this R and R and R, and so on. These are all exactly the same value of resistor. So if we move the wiper from position 0 to position 1, and then we trace the current, we see that we travel through exactly 1 resistor. So when we're in position 1, the resistance equals 1 times R. If we move this wiper to position 2, and we trace the current path, we see it goes through 2 resistors. And so in position 2, the resistance equals 2 times R. And likewise for 3 and 4 and 5, so that when we get to position 5 with our wiper, for example, we now travel through 1, 2, 3, 4, 5. So our resistance in position 5 is equal to 5 times R. So now let's put values on these resistors. So instead of R, let's call these 1 ohm. So each of these is now a 1 ohm resistor. And on and on. So when we're in position 0, we go through no resistors, and our resistance is still 0. When we're in position 1, we go through a single resistor, and our resistance is 1 ohm. We go through 2, it's 2 ohms, 3 ohms, 4 ohms, 5 ohms, and so on. And so that would be our first switch. Our second switch would be wired exactly the same way. The only catch is that now we're using 10 ohm resistors. And we use 9 of them. And so when we're going through position 1, when we're in position 1, we're going through 10 ohms. Position 2 is 20 ohms and 30 ohms and 40 ohms and 50 ohms. So our second switch gets wired the same way with 10 ohm resistors. Our third switch gets wired with 100 ohm resistors. Our fourth switch with 1,000 ohm resistors. Our fifth switch with 10,000 ohm resistors. Our sixth switch with 100,000 ohm resistors. So each of the switches gives us a selection, the ones place, the tens place, the hundreds place, and so on. And every one of them is wired the same. The only difference is the resistor values. So now how do we hook these up to make it all work together? Well, if we consider each of our switches as having terminals, I'm not going to draw all 10, whatever it comes out to be. You know there's 10 of them there. And then we have our resistors coming off here, so on and so forth. And we do the exact same thing with the second switch here. And let's say this is going to be our ones place. This is going to be our tens place. And again, so what we're going to do is we're going to simply, this is going to be one terminal, and then we're going to wire the switches in series. And so on to the third switch, and the fourth, and the fifth, and the sixth, and then when we get to the last switch, we're going to come out with another terminal. So you can see now that these are in series. So if I select this wiper for 2, I get 2 ohms, if these are 1 ohm apiece. And if I select this wiper in position 2, these are 10 ohms apiece. We trace the current path, 20 ohms plus 2 ohms. That's set for 22 ohms. And so we're going to do that for all 6 switches. So if you take a look at the website, theelectronicshobbyblog.com, and you look up our Let's Build project for the resistance substitution box, you'll find the entire schematic, including all of the resistor values. Well, that does it for this time. Join me next time when we'll go online, select appropriate components, and place an order. The next episode should be up online in the next few days. See you then.